Let's take a look at Le Chatelier's principle and how it applies to an equilibrium system. So this principle says that if you make a change to a system, so if you make some sort of stress on a system that's already at equilibrium, the system will shift to try to reestablish that equilibrium, to try to relieve the stress. So a comparison you can make is that if you're in a car and you go around a curve kind of fast and you feel yourself getting pulled to the right, you're going to lean to the left so that you can keep sitting up straight. So, the pull to the right, you lean to the left to counteract that pull. So that's what the system is doing. If you stress the system in one direction, it's going to respond to the stress to try to reestablish that equilibrium and undo what you've done. So the system is always going to try to undo what you have done. So what could you do to it? You could change the concentration of the reactants or the products, either by adding stuff or taking it away. Remember, a system that's at equilibrium has this equilibrium constant, that is the concentration of the products over the concentration of the reactants. And this value, we didn't look at the values too closely, but the value of KEQ for any given equilibrium is a constant. It's always the same. So if you change one of these values, the system's going to have to respond to reestablish the correct value for KEQ. So if you add products and you make this numerator too big, the system is going to have to take away some products to bring it back down. If you take away something, take away reactants, let's say, then the system's going to have to make more reactants in order to make KEQ be the right value. Okay, so here we have an equilibrium system. Nitrogen and oxygen are the reactants. NO, or nitric oxide gas, is the product. So if we add N2, we are making the amount of N2 go up. So the system is going to have to do something to make the amount of nitrogen go down. So how would the system make the amount of nitrogen go down? Well, it could take that nitrogen and use it in the reaction, the forward reaction, to use up nitrogen and create NO. So what would happen is that the forward reaction would speed up. You've put in more nitrogen, it's going to take away the nitrogen. So it's going to shift. We call this shifting the equilibrium to the right. So it's going to shift right towards the products. It's going to use up the reactants and make more products. Let's try a different scenario. For B, we have some NO that's being added. So we are increasing the amount of NO gas. And so the equilibrium is going to want to respond by decreasing the amount of NO gas. And the way the system can take away what you've added, it can take away that NO gas by speeding up the reverse reaction, taking some of that NO and breaking it up into nitrogen and oxygen. So you've added some, the system is going to try to take it away. When the reverse reaction is speeding up, we call that a shift to the left, or a shift towards reactants. So what's happening is that the equilibrium, instead of being a balanced rate forward and backward, it has to speed up the backward reaction relative to the forward reaction. So this is going to drive things in this direction. So this would be a shift to the left. So for this third possibility, we are going to remove oxygen. So we are taking this amount of oxygen and making it go down. The system is going to want to respond by building the level of oxygen back up. We've taken some away. The system is going to make more. How does it make more oxygen? By taking NO and increasing the reverse reaction to make nitrogen and oxygen out of the NO gas. So this is going to be a shift to the left as well. So we can call this a shift to the left or a shift towards the reactants. How would an equilibrium system respond to a change in temperature? Well, to figure this out, something that works pretty well is to write the energy as a reactant or a product. If energy is being consumed, we say that it's a reactant, or we write it with the reactants. If it's being produced, then it's one of the products. We write it with the products. So let's look at this reaction over here. The change in energy is a positive 357. That is an endothermic reaction. We're putting energy into the reaction to make the products. The products are higher in energy. Since we have to put energy into the reaction, we can write it as one of the starting materials, one of the reactants. We have to put HF into this reaction, we have to put chlorine into this reaction, and we have to put our 357 kilojoules into the reaction. So the 357 kilojoules is like one of these reactants over here. If we are reducing the temperature, we are taking away heat. So we're taking away heat, we're taking away thermal energy. So here is our energy, it's one of our reactants. If we make it go down, the system is going to respond by trying to make it go up. So we've taken away heat, the system is going to try to make more heat. The heat is on the reactant side, the left side of the reaction. So in order to make more, this reaction is going to have to shift to the left. So just as if you took away chlorine, or if you took away hydrogen fluoride, the reaction would have to shift left. If you take away heat, the reaction will also have to shift left here. For this next example, we have a negative overall energy change. So our products are lower in energy than our reactants. This is an exothermic process when energy is coming out of the reaction. So if energy is coming out of the reaction, the energy is one of our products. So we can write the energy on the right side of this reaction. Reacting nitrogen and 3 hydrogen, 1 mole of nitrogen and 3 moles of hydrogen produces 2 moles of ammonia and 92 kilojoules as one of the products. So if we reduce the amount of heat, if we take away heat, then the reaction is going to have to make more heat, and this equilibrium to make more heat goes to the right. So in this reaction, the heat is on the right side of the reaction. If we take away heat and the system wants to make more heat, it has to go to the right. That's where the heat is. Okay, so for this third one, we are not given a value of our delta H. We're just told that this is an endothermic reaction. That means that heat is being put into the reaction, and heat is one of the reactants. It's one of the starting materials. So since heat is one of the reactants, we'll just write it on the left side of the equation. So if this is an endothermic reaction, you have to combine some heat and some oxygen in order to get the product, which is ozone. O3 is ozone. Okay. So if we are perturbing the system by taking away heat, the system is going to want to respond by building up heat. To make more heat, the reverse reaction has to occur. If we want to make more heat, we have to shift it to the left because the left is where the heat is. So this is kind of consistent. Our first example was an endothermic reaction. We needed to shift left. Then we had an exothermic reaction. We had to shift right. Now we have an endothermic reaction. We have to shift left. This last one lists the heat as one of the starting materials, one of the reactants. So this is also an endothermic reaction. The forward reaction is absorbing heat. The reverse reaction is what is releasing heat. So if we take away heat, the reaction that can make more heat is the reverse reaction. So it's going to have to shift to the left to make more heat when we've taken the heat away. Okay, so changing volume is a little bit different from changing temperature. So now we're not going to care whether the reaction is endothermic or exothermic. We are going to care about the number of moles of gas on each side. Changes in volume affect gases a lot more than liquids or solids. If you compress gases, the volume can change. If you squeeze on liquids or solids, the volume doesn't really change that much. So gases are most affected by changes in volume. So if you think of volume as the space you have and the moles of gas as the stuff you have, you can think about this as changing apartments. If you downsize your apartment, if you move into a smaller apartment and you reduce the amount of space that you have to get rid of some of your stuff somehow. Have a tag sale, put it in storage. You have to do something to get rid of your stuff. So if you've reduced the amount of space, you're going to have to reduce the amount of stuff by shifting towards the side that has fewer moles of gas. If on the other side you move into a larger space, a larger apartment, then what do? You usually go out and buy more stuff. So you're going to fill the space with more stuff. If you have more space, you'll get more stuff. So you're going to shift towards the side with more moles of gas. All right, I scrolled up so we can see all of these examples. Let's count the moles of gas on each side. It looks like all of these reactions are entirely gas, so we can just count everything. This side has 3 moles of gas, 1 of hydrogen fluoride, 2 of hydrogen fluoride, 1 of chlorine. And this side has 3 moles of gas, 2 of hydrogen chloride and 1 of fluorine. So if you have the same amount of gas on each side, then changing the volume is not going to make any change. So it's kind of like you're moving to, a same size apartment. Then you don't get rid of your stuff and you don't buy more stuff. So there's no shift here. Here you have a system, an equilibrium that has 4 moles of gas on the left and 2 moles of gas on the right. So here on the left, 1 mole of nitrogen, 3 moles of hydrogen, altogether 4 moles. So we are reducing the volume here. We have less space, and so we're going to choose less gas in order to occupy that smaller space. So this would be a shift to the right. We're going to have to save space by taking some of these 4 moles of gas and making it into 2 moles of gas and reduce the amount of space that we need because we've reduced the amount of space that we have. All right, we have a similar situation here in that there are more moles of gas on the left than on the right. So if we need to save space, this one will also shift to the right. And this one we have 2 moles of gas on the left and 2 moles of gas on the right. So changing the volume is not going to make any shift for this equilibrium. All right, so the last thing we can do is add a catalyst to an equilibrium. And remember, a catalyst speeds up a reaction by reducing the activation energy. So here I have a sample reaction. We have this, so we have this green arrow representing the amount of activation energy that takes place when you go in the forward direction. We have this larger burgundy arrow representing the activation energy you need when you go in the reverse direction. If you have a catalyst, what it does is stabilize the intermediate. It just kind of lowers these curves. It flattens this hill over here. And so both of these activation energies are lowered, and both the forward and reverse reaction rates speed up. So the result of this is that an equilibrium can be established faster, but as far as the amounts of reactants and products, that does not change. So there's not really a shift in the amount of reactants and products that you have in your equilibrium. It just makes it easier and faster to get to that equilibrium. So let's take a look at this last example problem. We'll pull it all together and we'll just use this one equilibrium system and try all different kinds of changes, all different kinds of stress that we could put on this system and predict how the system is going to respond. So this first one here, we're increasing the temperature. So we are building up the amount of heat. And what the system is going to want to do is take some of that heat away. And the way that it can take away heat is to go to the left. There's heat on the right, so if we want to take away that heat, we have to use it up and go to the left, do the reverse reaction. If we increase the volume, that shift would be based on the number of moles of gas. So let's count those. On the left, we have 2 moles of gas, 1 carbon monoxide and 1 water. And on the right, we have 2 moles of gas, 1 carbon dioxide and 1 hydrogen. And since we have the same number on both sides, volume changes are not going to cause a shift. For this one, we are adding hydrogen, which is one of our products. So if we're adding a product, the way the system can respond to take away the product is by shifting to the left. The reverse reaction will use up that hydrogen and take it away. We just mentioned how adding a catalyst speeds up both the forward and the reverse reaction, so there's no overall shift either to the left or the right. So for removing CO2, that's one of our products. So if we remove CO2, the system is going to want to build up more CO2 and replace it. The way the system can replace the CO2 is by increasing the forward reaction, taking the carbon monoxide and the water and making more CO2. So it's going to bring things in this direction and shift to the right. If we add water, the system is going to want to respond by taking away the water and using it up. If it's using up the water, then that is the forward reaction. It's going to push it to the side where the water has been reacted and is gone. So that is a shift to the right. And then finally, if we're removing the carbon monoxide, then the system is going to try to make more by shifting left. The reverse reaction will make more carbon monoxide. So these are the ways that the system would respond to each of these stresses on the system.